Okay, so today in this lecture we will complete the proof of the linear lower bound for the randomized complexity of disjointness. So let me just recap what was already done, right? So it's the same PDF. The entire proof is there in the same PDF. So the goal is to find a distribution such that for an error epsilon, that the distributional complexity um, is at least linear. So um, and the Babai-Frankel-Simon theorem cannot be uh, the same distribution cannot be used because that's a product distribution, and product distributions are limited by this because there's an algorithm for all the product distributions, the square root and log in algorithm for all the product distributions. So hence we will this will use a another distribution. So the distribution is that both Alice and Bob get L length sets, L size sets. So where n is 4L minus 1, such that either the sets are disjoint or they are barely intersecting. So that makes it kind of hard for Alice and Bob to distinguish whether it's disjoint or not. So either they're disjoint or they intersect in exactly one element. Right. So the way we cast it here is that the partition we choose a random partition that is a of two sets of size 12 minus 1 and one singleton element I, and Alice's input X comes from T1 union I, so it's an L element subset of T1 union I, and Bob's input Y comes from T2 union I, an L element set of T2 union I. So if they intersect in the element I, and if they don't, that's fine. And we first had this corruption bound kind of argument, this lemma, and using this we proved the theorem, and then we proved the lemma one. The roadmap of lemma one was as follows. We first defined this parameters called row t, column t, etc. And this indicate how much does each partition contribute to the rectangle. Meaning how much weight, how much measure does the partition T bring about to this rectangle. So we see now we are on the way to proving this lemma. So we want to estimate what is B intersection R, measure of B intersection R, and measure of A intersection R. So how much does each of these partitions T that contribute to the measure? These are defined by the terms row T, column T, etc. Then we talk about good partitions that help us prove the lemma, or in equivalently bad partitions that don't assist in proving the lemma. So we make the definition, and we claim that most partitions are good. The contributions from the good partitions are significant, and using that we relate the expectation of row 0t, column 0t with mu of A intersection R, and row 1t, column 1t with mu of B intersection R, and combined with the definition of good and bad. Putting all this together, we get the lemma statement, which is again mu of B intersection R is at least alpha times mu of A intersection R minus 2 power minus delta n. Just to recap, mu of B intersection R is a fraction of contribution from the 0 inputs, and this is the contribution from the 1 inputs. Mu of A intersection R is a contribution from the 1 inputs. Okay, and that's what we want to show. So this is, and what we went through the entire proof of lemma except for the proof of claim 1. So today that's what we will show. Again, this is the definition of row t, row 1, row 0 t, row 1 t, and so on. Okay, so I guess we'll just recap things as and when we need them. That's all of this is done. So now let us go to the proof of claim 1. So claim 1 stated that for all T2, right, probability of bad x t equal to 1 given T2 is at most 1 by 5. What does this mean? This probability is for a fixed T2, and the probability is over all the partitions such that the T2 value is fixed. So just as a thought exercise, how many such partitions are there? once you fix a T2, there are 2L minus 1 elements that have been fixed as T2. The remaining 2L elements are there. How many partitions are there? It is just about fixing the I. Once you fix I, the partition T is entirely fixed. Out of 2L elements, we need to pick one element as I. So there are 12 elements here, and there are 12 partitions here, and they are all uniformly chosen. Okay? And we are estimating the probability that bad x t is equal to 1. But this is just an indicator random variable that t is x bad. So we are asking, once you fix t2, what is the probability that t is x bad? And we are claiming that is at most 1 by 5. Okay. So observation 2 states that once you fix t2, the value of rho t is fixed. So you may recall, once you fix t2, observation 2 states that rho t is fixed, as well as column 0 t is fixed. Okay. So rho t is fixed for any partition t that comes that has a fixed t2. Now suppose the rho t is at most 2 power minus delta n. Okay. In such a case, now rho 0 t is at most 2 rho t. This follows from observation 1. Observation 1, rho t is equal to half of rho 0 t plus rho 1 t. So rho 0 t is at most 2 times rho t. So yes, so rho 0 t is at most 2 times rho t. But this is a fixed number, and we know that this is at most 2 power minus delta n. So it is 2 times 2 power minus delta n, right? And now rho 0 t divided by 3 minus 2 power minus delta n. So this is 2 power minus delta n, 2 times 2 power minus delta n divided by 3. So this will be less than this, and hence this is negative. And rho 1 t is, it's a probability. Rho 1 t is a probability, and hence rho 1 t will be, it will be non-negative. So you can get this. So what does this mean? Rho 0 t divided by 3 minus 2 power minus delta n less than or equal to rho 1 t. Right? So what is that? That means that it is not x bad. Right? If it is x bad, then rho 1 t would be strictly less than this. But now we have the opposite condition. So that means t is not x bad. So what we have is that t is not x bad. If rho t is such that rho t is less than or equal to 2 power minus delta n. So it is not x bad, so which means bad x of t is equal to 0. So all that we have used till now is, if t is such that rho t is less than or equal to minus delta n, right? Right. So for where t2 is like this, then bad x t is equal to 0. So the probability that bad x t is equal to 1 is also 0. Right? We know this is 0. So for those t2, this is 0. So it is less than 1 by 5. So we are done. Now we need to consider the case when rho t is greater than 2 power minus delta n. And that contributes to the majority of the proof. So now let us try to understand rho t and rho 0 t. So what is rho t? Okay, let us go back to the definition. Rho t is the probability that x is in C given t, and rho 0 t is the probability that x is in T given t and I is not in x. Rho 1 t is the probability that x is in C given t and I is in x. Okay. So let us try to understand the probability. So to understand that, we'll first define the set S, capital S, which is a set of all x are the rows, which are in C of length L, such that x is contained in T1 union I. Okay, so this is an I. When I scanned it, the dot above the I did not appear. This is not 1, this is I. In other words, S is a candidate element that has non-zero measure in the rows, but it's also included in C. C is the rows corresponding to the rectangle R. And T1 union I is everything that is not there in T2, right? So this is, even though we have not fixed T or T1 or I, T1 union I is already fixed because T2 is fixed. So S is all the X's that are in C that are in that can be chosen by the distribution with non-zero measure. So what is rho T? Rho T is a probability that X is in C given T. So basically, each one of these are likely to be chosen by the distribution. And how many of such items are there? So T2 is fixed, so the remaining 2L elements are there for choosing. So 2L choose L elements are there, out of which C contains a subset of them, and those subset is given by S. So rho T is nothing but the size of S divided by the total number of possible rows that you could have chosen. So which is 2L choose L. So rho T is S divided by 2L choose L. Now let's fix T1 and I, meaning fixing the partition T. Now let us consider how many of them contribute to row 0T. Row 0T, remember, are those which do not have I in them. Okay. So let us define, which means they are entirely contained in T1. So let us define, to understand row 0T, let us define S prime, which is a set of all the rows which are in C of length L, which are entirely contained in T1. So even though I use T1 here, this did not require fixing of T1, because T1 union I is nothing but every n minus T2, but now this requires fixing of T1. So let us understand row 0T. Row 0T is a set of all X in C such that T, the partition for a given partition T, and I is not an X. So in other words, it's a fraction of elements in S prime divided by the total number of such sets, which is the size of S prime divided by 2L minus 1 choose L. This is the actual number of elements that are there in C, which contribute to the measure, divided by the total number of elements that contribute to the measure, 2L minus 1 choose L. So row 0, this is row 0T. But I can write this as, I can add and divide and multiply by S, divide and multiply by 2L choose L. So now I get S prime divided by S, size of S prime divided by size of S. Size of S divided by 2L choose L. 2L choose L divided by 2L minus 1 choose L. Now this one, size of S divided by 2L choose L, is already calculated as rho T. And this, if you just write down the binomial coefficients, you will get that it is nothing but 2. So now rho 0T is fraction of S prime divided by size of S prime divided by size of S times rho T times 2. Okay. Now, suppose you choose a set small s from the set capital S. What is the probability that I is not an S? Where the probability is taken over all the choices of small s from capital S. Okay, so capital S contains all the elements in S. What is the probability that you will get end up getting an element in S prime? So it is just the fraction of the size of S prime divided by the fraction of size of S. That is the probability that I is not in S. Where the probability is taken over small s is uniformly chosen from capital S. We have already seen rho 0T is twice rho T times S prime divided by S. Now we can replace S prime divided by S as probability of I not in S, where the probability is taken over all the small s coming from capital S. Till now it's been all probabilities and setting up stuff. Now let us slowly get into the proof. Similarly, we can say that rho 1T, again this is very similar calculation, or We can also use the earlier defined equalities where we saw that rho t is equal to half of rho 0 t plus rho 1 t. So if you were using that to work out, then you'll get that rho 1 t is 2 rho t into 1 minus probability of I not in S, but 1 minus probability of I not in S is the probability that I is in S. So you get this. Rho 1 t is twice rho t times probability of I is in S, where S is chosen, small s is chosen uniformly from capital S. Okay. If t is x bad, then this is the condition. Then it needs to satisfy that rho 1 t is at most rho 0 t divided by 3 minus 2 power minus delta n. So we can write this as well. This is a slightly looser bound. Now I can replace rho 0 t and rho 1 t with these these expressions, and 2 rho t cancels from both ends, which means we get that probability I in S is strictly less than probability I not in S divided by 3. Now adding probability I in S divided by 3 to both sides, you'll get this. But now this quantity is 1. So the RHS is 1 by 3 multiplied by 1, and LHS is 4 by 3 times probability I in S. So you can bring down the 4 here to get that probability that I in S is at most 1/4. So if t is x bad, the probability of I is in X is at most 1/4. Let's just recap. We first took care of the case when rho t is at most 2 power minus delta n, in which case the bad t was 0 and the probability of bad t equal to 1 is also 0, and hence this inequality is satisfied. Now let us go to the more involved case of rho t greater than 2 power minus delta n. Then we write the sets S that contribute to rho t and S prime that contributes to rho 0 t, and it is a set of all and then you write rho t in terms of size of S divided by the size of all the set of all possible choices. It is 2L choose L. Rho 0 t similarly, we get this in two equations. Rho 0 t is this twice rho t times probability of I not in S, and rho 1 t is twice rho t times probability I is in S, where the probabilities are where small s is chosen from capital S. And if t is x bad, we get the inequality that the probability that I is in S is at most 1/4. Right? Okay. So now let's say without loss of generality, right? T2 is fixed. Let's say T1 union I is the set 1, 2, 3, etc. up to 2L. We need to prove this for a fixed T2. So let's say T2 is fixed number. T2 is anything bigger than 2L plus 1. 2L plus 1 and the bigger number. So T1 union I is this. So let S1, S2, etc. S2L be the random variable. So now we'll work with this probability that small s is chosen from capital S. Be the individual random variables that. So what is the composition of small s? Small s is a set of size L. What is the composition of small s? So we said we have one random variable for each of these 1, 2, 3 up to 2L. So S1 is 1 if 1 is in small s, S2 is 1 if 2 is in small s, S3 is 1 if 3 is in small s, so on. S2L is in 1 if 2L is in small s. So each of Sj is 1 if j is in S, and 0 if j is not in S. So how many Sj's are equal to 1? Exactly L of Sj's will be equal to 1 because the size of small s is equal to L, and exactly L of Sj's will be equal to 0. So that means that the Sj's are not really independent, because if S1, S2, S3, etc. SL is all ones, then everything else must be zeros, because we can only have L of them as 1. So they are not independent, certainly. Okay. So now let's assume that we'll assume for contradiction that probability of bad x t is bad x t equal to 1, but that is the same thing. Bad x t is greater than 1/5. Okay. So given T2, as like I already said, once T2 is fixed, the choice of I fixes the partition T. The choice of I fixes this. So basically there are 12 choices for I. And out of these 12 choices, if this means that probability of bad X is greater than 1/5, means that for 1/5 of the fractions of the choices, 1/5 of the 12 choices, we have a T that is X bad. Bad X T is equal to 1 for 1/5 of the choices. And for such I, we have already seen that if T is X bad, the probability that I is in S is at most 1/4. So for at least 1/5 fraction of I, we have a T that is X bad. And for those I, we have probability that I is in S is at most 1/4. Okay, now so that's all we need. Now it's all about something called entropy calculation. Okay, so this entropy is not the it's kind of like, it's similar to the thermodynamics entropy, but it's slightly different. So if you can check Wikipedia for Shannon entropy or the entropy in information theory. So basically, it's the amount of information that is contained in some randomness, and we have already seen it in one of the proofs where we just stated that h of x is equal to minus x into log of x plus 1 minus x into log of 1 minus x. So basically, it is defined for things that can be random, and it measures the amount of information. So, for instance, you can look up the definition of entropy. You can pause the video, for instance, and look up the definition. So, the entropy of a random variable that is, let's say, 90% 1 and 10% 0 is low. But the entropy of a random variable that is 0 with half probability and 1 with half probability, that is 1. So basically, the closer it is to half, 50-50, the entropy is higher. And the maximum entropy of a 0-1 random variable is 1. And the entropy becomes closer to 0 when the probability of the random variable becomes the probability of it being 0 is high, or the probability of it being 1 is high. And you can also talk about different choices, number of choices that you want to make, and the entropy of multiple choices. Let's say you have 2 bits, both of which can be 0 and 1, so that the entropy will be roughly the sum of them if they are independent. If they are dependent, then the entropy will be at most the sum. Anyway, you can look up all this, and we can discuss it in the live sessions. So the entropy of such I, where I is the probability of I is in S is at most 1/4. We know that for these I, the entropy is, so this is just the formula of entropy. Entropy is denoted h of x is minus x into log of x, where log is to the base 2, plus 1 minus x into log of 1 minus x. The minus is for everything. And if you set this to be 1/4, you can calculate this. This comes out to be roughly 3.81 something. So I'm upper bounding it by 0.82. So if the probability is less than 1/4, then the entropy will be even smaller than this, because the entropy increases till half and decreases after half. So for 1/5 fraction of the i's, for the SJs, we have the entropy is 0.82. For the remaining SJ, we will just take the trivial upper bound for entropy, which is 1. And h of s, so for the entire vector S1, S2, etc. If this were independent, this would be the h of s will be equal to the sum. But since they are dependent, the sum turns out to be an upper bound. The entropy is at most the sum of this. And what do we know? We know that for 1/5 fraction of Sj, we have this upper bound. So there are 12 Sjs. So 12 by 5 a fraction of this is upper bounded by 0.82. For the remaining, we don't have any bound, so we'll just take 1. So the remaining 80% is upper bounded by 1. So we can write this. Now this, if you add it up, this is enough to, we'll get something like 1.928 L. So the entropy of HS, which is the entire vector, is 1.928 L. So this is also related. So and now we will calculate the same entropy in another way. What is the size of S? So remember, the number of such vectors S1, S2, S2L is actually the number of such valid sets S. What is the number of what is the size of such? What is the number of such sets S? The number of such sets S. You remember, we showed that size of S, the number of such sets smallest. So smallest is the number of comes from capital S. So capital S is the set of all such possible vectors. It is given by 12 choose L times rho t. So it's 12 choose L times rho t, which is, and we know that we are in the case when rho t is at least 2 power minus delta n. The other case was easy and we already saw that. So we get that this is at least 2L choose L times 2 power minus delta n. Smallest is uniformly chosen from capital S. Now we can then the entropy of smallest is actually the log of this. So when you have an object, let's say smallest capital S was of size 32, the entropy of smallest would have been log of 32, which is 5. So you can see the correspondence. So if capital S was all the 5-bit integers, where each bit can be uniformly chosen 0 or 1, then the entropy will be 1 plus 1 plus 1 plus 1 plus 1, which is 5. And you can look at the number of possible smallest, which are all of, which is 32. So log of 32 is also 5. So that is the rough idea why this is true. So now what is log S? From this log of size of S can be, we can see it's log of this is at least this. And now we use our very familiar Stirling's approximation. 2L choose L is roughly 2 power 2L divided by square root of pi L. So this is L, sorry for the smudge here, times 2 power minus delta L. Now I can write it as 2L uh, 2L from here, the power of 2, minus delta n from here, minus log of square root pi L. So this follows by Stirling, you can work out. We have seen enough exercises. And now for the power of 2, it's 2L minus delta n, and for the rest, it's minus log square root pi L. And recall that n is nothing but 4L minus 1. So I can write this as 4L minus 1. And once I take out L outside, you get 2 minus 4 delta here. And then you have minus log square root pi L divided by L minus some delta divided by L. So basically some sub-constant thing, log square root pi L divided by L minus 1 delta divided by L. So this is sub-constant thing which I am denoting by this little o of 1 because it's sub-constant. So basically this is the entropy calculated in another way. We know that the entropy is at least this. But we know that the entropy is less than or equal to this also. So we know that this is a lower bound on or upper bound on the entropy, and this is a lower bound on the entropy. And so now if the entropy is at least this and at most this. So the point is that if delta is very small, let's say delta is 0.01, then for large value of L, this will be like 1.96 and this will be very, very small, negligibly small. And hence you will get this quantity greater than this quantity, which is a contradiction. So if delta is small, then we get a contradiction. And this contradiction is to the fact that the assumption that we made here, the probability of bad x is greater than 1/5. Okay, so let me recap the proof again. We first for rho t less than 2 power minus delta n, it was easy to see. For rho t greater than 2 power minus delta n, we first identified capital S as a set of all x, which are Alice's inputs, and all S prime, which are all Alice's inputs which don't contain I. So the rho 0 t could be written as size of rho t could be written as size of S divided by 2L, choose L. Rho 0 t could be written as size of S prime divided by 2L minus 1, choose L. And we wrote rho 0 t and rho 1 t in terms of these probabilities, where probability twice rho t times probability that S is in S, probability I not in S. Rho 1 t is twice rho t times probability of S in S, I is in S. And if t is x bad, we get that probability that I is in S is at most 1/4. And now we have random variables for each of these elements. So assume that T1 union I is 1, 2, 3 up to 12. For each of these elements, we set random variables S1, S2, etc., S2L, 0, 1 random variables. So let's assume for contradiction that bad x t is x bad with probability at least 1/5. This means that the probability is over the choice of t. So there are 2L possible, so which means the choice of I, because T2 is fixed. For 2L such choices, or 1/5, for at least 1/5 of these 2L choices, we have a t that is x bad, which means for those t, the probability that I is in S is at most 1/4. And for those Sj, we have the entropy of Sj is less than the entropy of 1/4, which is 0.82. For the remaining Sj, the entropy is at most 1. Now we can consider the entropy of the entire 2L sized bit string, which is at most the sum. So if they're independent, this would be exactly the sum. Since they're dependent, the sum forms an upper bound. And we get, so we know that 2L of 1/5 of them is upper bounded by 0.82 and the rest is upper bounded by 1. So you get it's 1.928. So it is sufficiently away from 2. That's all that matters. Now we directly compute the entropy of S by looking at how many options are there for small s. So the number of possibilities of small s is the size of capital S, because small s is chosen from capital S. What is size of capital S? It's 2L choose L times rho of t. And we know that rho of t is at least 2 power minus delta n. So h of S is at least this, and log of the size. And we can get this upper bound, lower bound. So we have that h of S is at least this and at most this. Right? So h of S is something between this and this. But this lower bound is way more than the upper bound when we set delta to be something very small. And that forms a contradiction. So we never, so we can set delta to be something significant, like 0.01, and it will not contradict anything. We haven't relied on anything any other properties of delta except that it is small anywhere else. So by setting delta to be something very small, we get a contradiction, because HS is upper bounded by 1.93L but lower bounded by, let's say, 1.96L or 95L, and that proves that that proves a contradiction to the fact that, to the assumption that the bad x is at least 1/5. So the probability of bad x is at most 1/5, and that completes the proof of claim 1, which completes the proof of the linear lower bound for the randomized complexity of disjoints. Okay.